Darkness was not just the absence of light. It was a state of space, a dense, hot, boiling medium in which there were no stars, no structures, and no familiar forms of matter. After the birth of the universe, matter was in the form of an almost homogeneous plasma ocean. In this environment, future differences were already hidden. Tiny fluctuations in density, subtle deviations that became the seeds of all subsequent cosmic diversity. When the universe cooled enough for protons and electrons to combine into neutral atoms, light was able to propagate freely for the first time. Space became transparent, but it remained shrouded in darkness, an era known as cosmic darkness. During this period, there were no sources of light, only slowly growing inhomogeneities, which began to increase under the influence of gravity.
Gravity did not act instantaneously or chaotically. It gradually collected matter into denser regions. Dark matter, invisible and not interacting with light, played a key role. These structures grew, merged, and intensified, creating the first rudiments of future galaxies. The gas, falling into such gravitational traps, was compressed and heated. However, for the formation of stars, compression alone was not enough. Cooling was necessary. The early universe lacked heavy elements, so cooling occurred through molecular hydrogen, one of the few available mechanisms for energy loss. This allowed the gas to collapse further, reaching densities at which thermonuclear reactions began. This is how the first stars lit up. They were different from modern ones. Massive, extremely hot, short-lived. Their radiation was intense and harsh, capable of ionizing the surrounding gas.
The first galaxies formed not as stable structures, but as dynamic, turbulent systems. They consisted of small clusters of stars, gas and dark matter, constantly interacting and merging. Their shape was far from the usual spirals or ellipses, but rather chaotic, irregular clouds, in which the processes of star formation took place with great intensity. Mergers played a decisive role. Small proto-galaxies collided and merged, forming larger systems. During these interactions, powerful bursts of star formation occurred. Gas was compressed by shock waves, forming new generations of stars. These events gradually led to the growth of galaxies, an increase in their mass, and a more complex structure.
The first galaxies were compact. Their sizes were much smaller than today's, but the density of matter inside them was much higher. This created the conditions for frequent interactions between stars and gas clouds. The energy released during the birth and death of stars greatly influenced the evolution of such systems. When massive stars ended their lives, powerful explosions occurred, supernova. They threw heavy elements into the surrounding space that did not exist before. These elements became the building blocks for subsequent generations of stars, changing the physics of gas cooling and speeding up the formation of structures.
Gradually, the chemical composition of the universe became more complex. The first galaxies became sources of enrichment of the intergalactic medium. The gas emitted from them spread into space, affecting neighboring areas and participating in the formation of new systems. The radiation of the first galaxies played a key role in global processes. Streams of ultraviolet light ionized hydrogen in the intergalactic medium, converting the neutral gas back into plasma. This process propagated in waves until most of the universe became ionized. It was one of the most important transitions in the history of space. The structure of the first galaxies depended on many factors. the mass of the dark matter halo, the rate of gas accretion, the intensity of star formation, and feedback from stars.
Feedback included radiation, stellar winds, and supernova explosions, which could both stimulate and suppress further star formation. Some of the first galaxies may have contained the nuclei of supermassive black holes. These objects formed either from the collapse of massive stars or directly from dense gas clouds. Their growth occurred due to gas accretion and mergers. The active nuclei of such galaxies emitted huge amounts of energy, affecting the environment. Over time, there was a hierarchical evolution. Small structures combined into larger ones, forming galaxies similar to modern ones. In this process, traces of early stages were preserved: ancient stars, chemical signatures, dynamic features.
Observations show that as early as a few 100 million years after the expansion of the universe began, there were galaxies with a high rate of star formation. This indicates that the formation processes began very early and proceeded effectively. The cosmic web, a gigantic web of filaments and knots of dark matter and gas, served as the basis for the distribution of galaxies. The first galaxies formed at the nodes of this structure, where the density of matter was greatest. The filaments served as channels through which gas flowed into galaxies, supporting their growth. The temperature and density of the gas, turbulence, magnetic fields, all these factors affected the details of the formation. Even small differences in initial conditions could lead to noticeable differences in the evolution of individual systems. The first galaxies were not isolated. They existed in an environment saturated with interactions: gravitational, radiation, hydrodynamic. These interactions created a complex picture in which the formation of structures was a continuous process rather than a single event. Over time, the rate of star formation has changed. In some galaxies, they reached peak values, then decreased under the influence of feedback. In others, they were maintained at a high level due to a constant influx of gas. The evolution of the first galaxies led to a variety of shapes and types. Gradually, disks, central seals, and stable orbits of stars appeared. But in the early stages, instability, turbulence, and rapid change dominated.
Research shows that the first galaxies were key contributors to the formation of the large-scale structure of the universe. They not only grew on their own, but also influenced the surrounding space, setting the conditions for subsequent generations of objects. Each of these early systems was part of a vast process in which simple initial conditions led to an incredible variety of forms. From an almost homogeneous environment, structures capable of complex evolution, interactions, and transformations arose. It was in these first galaxies that the history of light, structure, and chemical diversity of the cosmos began, a process that continues, spreading through billions of years and filling the universe with increasingly complex forms of matter and energy. The gravitational nodes in which the first galaxies were born were not stable and complete structures. They continued to grow, absorbing matter from the surrounding cosmic environment. Streams of cold gas flowed along the filaments of the cosmic web, increasing the density of the central regions and fueling new bursts of star formation. Each such flow became a channel for the transfer of matter, linking distant regions of space into a single dynamic system. Inside these forming galaxies, the gas was not evenly distributed. It gathered in dense clouds, where the pressure and temperature reached values sufficient to start new cycles of star formation. These processes occurred quickly on a cosmic scale. A single burst of star formation could change the internal structure of the entire system,
redistributing energy and matter.
The radioactive and ultraviolet radiation from the first stars began to destroy the surrounding gas, creating bubbles and voids inside galaxies. These areas became zones of low density, through which radiation spread more easily. At the same time, shock waves from supernova explosions compressed nearby clouds of gas, triggering new episodes of star formation. Thus, destruction and creation went in parallel, forming a complex internal dynamic. Dark matter continued to be an invisible framework that determined the overall structure. Its distribution determined the form of gravitational potentials in which ordinary matter was forced to evolve. Even when the gas was heated or ejected outward, the dark matter halo kept the overall system from decaying, ensuring the long-term stability of nascent galaxies.
Over time, denser central regions formed inside some galaxies. There was an accumulation of gas and stellar mass, which led to an increase in gravitational pressure. These regions became the centers of future active nuclei, where supermassive black holes could be born. Their growth occurred due to the continuous absorption of surrounding matter, creating powerful sources of energy that affect the entire galaxy. Energy emissions from these central regions could heat the surrounding gas so much that it ceased to be effectively compressed. This temporarily suppressed star formation in some regions, redistributing it to more distant regions. Thus, the growth of the center and periphery of the galaxy were in constant interaction, creating a balance between the concentration and dispersion of matter. The first galaxies were also subject to frequent collisions. Their relative velocities and proximity in the dense early universe made such events commonplace. During collisions, there was a complex redistribution of the orbital motion of gas and stars, which often led to the formation of new structures, including protospiral shapes and elongated tails of matter. Each merger did not destroy the system, but transformed it. Gravitational fields were combined, strengthened, and the new structure became more massive and complex. As a result of such processes, large galaxies were gradually formed, capable of holding significant volumes of gas and supporting long cycles of star formation. Chemical evolution also played a key role. Initially, the universe consisted almost entirely of hydrogen and helium.
But inside the stars, nuclear reactions took place, creating heavier elements. After the death of stars, these elements spread into the surrounding space, changing the physical properties of the gas. With each generation of stars, cooling became more efficient, and the process of forming new structures became more diverse. Gradually, differences between galaxies emerged. Some retained high star-forming activity, while others moved to more stable states. Some lost a significant part of their gas due to powerful energy emissions, becoming more rarefied systems. These differences laid the foundation for the future classification of galaxies. The cosmic environment around galaxies also did not remain unchanged. Radiation and emissions of matter affected the intergalactic gas, heating it and changing its density.
This in turn affected the ability of new structures to form in neighboring areas. In this way, each galaxy became part of a wider network of interactions. Within these early systems, stable dynamic structures were gradually formed. The orbital motion of the stars began to regularize, the gas disks became more stable, and turbulence gradually decreased in some regions. It was a transition from a chaotic state to a more organized one, although full stability had not yet been achieved. The light of the first galaxies propagated into space, changing its state. Photon pressure, ionization and heating of the gas created large-scale effects that affect the further evolution of the universe. These processes ended the era of cosmic darkness, making the universe transparent and structured.
But even after that, the formations continued. Galaxies grew, collided, lost, and gained mass. Their evolution did not have a fixed point of completion, but was a continuous process of redistribution of energy and matter. Each of the first galaxies became the basis for subsequent structures. Their dynamics, chemical composition, and interactions laid the foundation for all further space development. From simple initial fluctuations, a complex network of objects arose, spanning billions of light years of space and continuing to change to the present day. In the early universe, the distances between forming galaxies were significantly smaller than in the modern era. Space expanded, but the density of matter remained high, so gravitational interactions occurred constantly.
Huge clouds of gas and dark matter intersected, collided, and deformed, creating giant regions of turbulence. Within these regions, new centers of attraction arose, around which future star systems began to gather. Gas moving through the cosmic web did not fall evenly into galaxies. Streams of matter swirled, creating rotation. It was this rotation that gradually formed the disk structures. But early disks were unstable. The tight knots inside them broke the symmetry, causing powerful gravitational waves. Such structures could have disintegrated, merged, or ejected huge masses of gas into intergalactic space. The radiation of young stars became more and more intense. Huge areas of ionized gas surrounded the first galaxies, expanding outward.
These regions collided with each other, gradually combining into giant bubbles of red-hot plasma. At some point, most of the intergalactic hydrogen was ionized. The universe finally came out of the age of darkness. But inside galaxies, the processes only became more complicated. Massive stars quickly used up their fuel. Their cores collapsed, creating neutron stars and black holes. Supernova explosions threw out colossal streams of energy that pierced the galactic gas in shock waves. Some areas were completely cleansed of matter. Others, on the contrary, were compressed even more. Heavy elements, synthesized in the depths of the first stars, began to change the very physics of the cosmic environment. Carbon, oxygen, silicon, iron, and other elements increased the efficiency of gas cooling. This led to the formation of more compact clouds and the birth of lower mass stars. Gradually, the universe moved from the era of giant primordial stars to more diverse stellar populations.
In some galaxies, particularly dense central regions were formed. Streams of gas rushed to the center, where huge masses of matter accumulated. Supermassive black holes were born there, whose mass grew at an incredible rate. Their accretion disks heated to extreme temperatures, emitting powerful radiation. Such objects turned galaxies into quasars, the brightest structures in the early universe. The light of the quasars was so intense that it surpassed the glow of billions of stars. Streams of energy were ejected over vast distances, creating relativistic jets, narrow jets of plasma moving at almost the speed of light. These ejections penetrated far beyond the galaxies, warming the intergalactic medium and affecting neighboring structures.
Despite the chaos, order gradually manifested itself in the universe. Galaxies began to spread along the filaments of the cosmic web. Between these filaments, there were gigantic voids,
regions of extremely low density of matter. Thus, a large-scale structure of the cosmos was formed, which has been preserved for billions of years. The young galaxies were extremely bright in the infrared and ultraviolet ranges. Huge amounts of dust produced by stellar explosions absorbed some of the light and re-emitted it at other wavelengths. This dust played an important role in subsequent evolution. It participated in the cooling of the gas and became the basis for the formation of more complex structures. In many early galaxies, real stellar storms were observed. The rate of star formation there was hundreds of times higher than in modern galaxies. Huge clusters of young stars created continuous streams of radiation, turning the internal environment into a red-hot, chaotic ocean of plasma and shock waves.
Some galaxies could not withstand such an intensity of processes. Powerful bursts of energy literally pushed the gas outward, depriving the system of material for further star formation. Such galaxies quickly faded away, moving into a relatively calm state. Others, on the contrary, continued to actively absorb matter from the surrounding space and remained highly active for a long time. Gravitational interactions between galaxies became more and more extensive. The first galactic groups and protoclusters appeared. In these regions, tens and hundreds of galaxies were connected by a common gravitational field. The gas between them was heated to millions of degrees, creating giant clouds of red-hot plasma. Within such clusters, continuous collisions and deformations took place. Galaxies were stretched by tidal forces, lost some of their stars and gas, and formed long streams of matter. Sometimes entire galactic structures were destroyed and swallowed up by more massive systems.
Dark matter continued to drive this process from the invisible depths of space. Its gravity held clusters together, shaped trajectories, and determined the future evolution of vast cosmic regions. Without it, galaxies would not have been able to form so quickly after the birth of the universe. Over time, some galaxies became more orderly. The rotation of the gas stabilized, spiral arms were formed, and the central bulges were compacted. Other systems remained elliptical, giant clusters of old stars with minimal gas. The differences between the types of galaxies gradually increased. But even billions of years later, the first stages of formation left traces. The oldest stars preserved the chemical composition of the early universe. The distribution of dark matter continued to follow the pattern of ancient fluctuations. The cosmic web retained the shape that appeared shortly after the appearance of the first galaxies.
Every modern galaxy bears traces of that ancient era when space was just beginning to fill with light. Inside the stellar halos, in the movement of gas, in the distribution of elements, the history of the early cosmos continues. The history of the transformation of an almost homogeneous universe into a gigantic system of galaxies, quasars, clusters, and intergalactic structures spanning boundless distances.
Billions of years passed, and space became different. The first galaxies, once small, chaotic clumps of gas and young stars, have evolved into giant structures that fill the cosmos with light. Some were swallowed up by larger systems. Others survived countless collisions and preserved ancient stellar populations in their depths. But even after huge periods of time, traces of their birth remained in the very fabric of the universe. The ancient light continues to move through space. Photons that left the first galaxies shortly after the end of the cosmic darkness are still crossing the expanding cosmos. They carry information about the time when matter was just beginning to assemble into structures.
when the first stars burned through the surrounding hydrogen with streams of ultraviolet radiation, and young black holes were already devouring matter at a monstrous rate.
These early galaxies changed the universe irreversibly. Before their appearance, the cosmos was almost uniform and dark. After that, the space was filled with light, heavy elements, magnetic fields, shock waves, and complex structures. A continuous cycle of the birth and death of stars, the redistribution of matter, and the formation of new systems began. Inside the first stars, elements were created without which the further evolution of the cosmos would not have been possible. Carbon, oxygen, iron, silicon, and a host of other atoms spread throughout galaxies after supernova explosions. They mixed with cold gas, became part of new generations of stars, planetary systems, and interstellar clouds. The universe gradually moved from the simplest chemical composition to an increasingly complex one.
Giant clusters of galaxies continued to grow. The cosmic web stretched along with the expansion of space, but its structure was preserved. Filaments of dark matter connected superclusters, and between them lay colossal voids where there were almost no galaxies. This network encompassed the entire observable cosmos, preserving the imprint of the earliest fluctuations that occurred shortly after the birth of the universe. Some ancient galaxies disappeared in the process of mergers. Their stars were scattered across larger systems, and the central black holes merged to create even more massive objects. During such collisions, space shuddered from gravitational waves propagating through the very fabric of the universe.
Even now, in the depths of space, extremely ancient galaxies continue to exist, whose light travels for billions of years. They look like shadows of an early era, compact, bright, filled with young stars and hot gas. Their observation allows us to see the universe as it was almost at the very beginning of its history. But the further the cosmos develops, the more its future changes. The expansion of space accelerates. Galaxies are moving away from each other faster and faster. At incredibly long intervals, many of them will be so far away that their light will never again be able to reach other regions of the universe. The cosmic web will begin to disintegrate into isolated islands of galaxies, surrounded by endless darkness.
Star formation will gradually weaken. Cold gas reserves will be exhausted. Fewer and fewer new stars will be lit inside galaxies. Space will slowly transition into the era of extinction, where only red dwarfs, neutron stars, white dwarfs, and black holes will remain. But the history of the first galaxies will never disappear completely. It will be preserved in the chemical composition of stars, in the distribution of dark matter, in the CMB radiation, and in the structure of the cosmos itself. Every galaxy that exists today bears traces of that ancient era when light first broke through the cosmic darkness.
It was then that the universe began to transform from a hot, almost homogeneous space into a complex ocean of structures, where gravity created giant star systems, collided with each other, gave birth to quasars, supernovae, and black holes. All modern cosmic diversity grew out of these first flashes of light in the midst of ancient darkness. The first galaxies were the beginning of the great transformation of the universe, a process that continues even today among endless clusters of stars, cold intergalactic voids, and distant lights moving through the eternal expansion of space.